my name is Caroline Jones, and my group and I will be proving the extended law of sines. Before we go over the theorem and the proof, though, let us first go over some important information that you'll need to know. Let us start with the law of sines. If you'll look at the blue triangle, triangle ABC, you'll see that A, capital B, and capital C all denote angle measures, and lowercase a, lowercase b, and lowercase c all denote the side lengths opposite those angles. I've also drawn an altitude from angle A and denoted it as h. If we go by the rule of sines, which if you take a sine of any angle measure, it's equal to opposite over the hypotenuse. So you'll see that with our blue triangle, we have sine of b is equal to h over c, and sine of c is equal to h over b. If we solve for h, we get that h is equal to c sine of b, and h is also equal to b sine of c. Since both of these equal h, they also equal each other. So we set them equal to each other, and then we can divide each side by sine of b and sine of c, giving us c over sine c is equal to b over sine b. Similarly, I've also drawn a pink triangle, triangle ABC, where capital A, capital B, and capital C denote angle measures, and lowercase a, lowercase b, and lowercase c all denote the side lengths opposite those angle measures. This time, though, I've drawn the altitude from angle B. And as I said, similarly, we get a over sine A is equal to c over sine c. Now, putting these two together, we get a over sine A is equal to b over sine b is equal to c over sine c. And that is the law of sines. Another thing you'll need to know about that before we can go on to the theorem and the proof is what a circumcircle and a circumradius is. The circumcircle, any circumcircle is unique to the triangle that it is drawn around. Well, any triangle can only have one circumcircle. So the circumcircle in this case is the orange circle that is drawn around triangle ABC. Now looking at the circumradius, we have the circumradius is the length of the radius of the circumcircle, and I've denoted that as r. And then one more thing, we also have a circumcenter, which is just the center of the circumcircle, and I've denoted that as O.
Hello, my name is Paul Lee, and for the extended law of sines, I will be going over the proof that every triangle has a unique circumcircle. But before we go through this proof, we'll first need to go over two different topics. The first topic is a definition of a perpendicular bisector. A perpendicular bisector is a line that forms a right angle with one of the triangle's sides and intersects that side at its midpoint. So there are two main components, and if you look at the figure, the triangle ABC below, you can see that this perpendicular bisector is a line segment that is a 90-degree angle. And then also, if you look at that point X, you can see that this bisector is located halfway between the segment BC on the bottom of the triangle. The second topic that we will cover will be the side-angle-side postulate. The side-angle-side postulate states that if you have a set of triangles that have two sides and an included angle in common, they are congruent. Using the side-side-side postulate, we can kind of use the same logic and prove the side-angle-side postulate. And to do this, we will just think of the side-side-side postulate. So we know that if all three sides of a triangle are similar to another triangle, those two triangles will be congruent. There is no other way the triangle could have a different shape or a different angle if the sides were not exactly the same length. So we know that if you have two sides that are the same, the length of the third side is only restricted by the angle opposite that side. If you look at the figure to the right, we see triangles ABC and DEF. For angle B, we can see the side opposite of it denoted lowercase b, and then for angle E, the side opposite for that one is denoted lowercase e. So if sides AB and DE are the same, and then BC and EF are the same, the only thing the third side can be depends on the angle that is opposite of it. And in this case, if we have angle B and E be the exact same angle, then the side lengths of B and E must also be exactly the same. Now that we have covered the definition of a perpendicular bisector and the side-angle-side postulate, we could move on to the proof that every triangle has a unique circumcircle. To do this, we will first create a triangle ABC. Within this triangle, we will construct perpendicular bisectors of sides AB and BC. These bisectors will intersect, and we can call that point O. So we know that OD is perpendicular to AB, and then we also know that OE is perpendicular to BC, since this is the definition of a perpendicular bisector. Furthermore, we can start comparing the triangles ODA and ODB on the top left part of the figure. We can say that OD is equal to OD through the reflexive property, and then we can also say that side length AD is equal to side length DB, since it is cut in half by the perpendicular bisector. And then also, we know that the angle measure of ADO is 90 degrees, and similarly, the angle measure of BDO is 90 degrees, which makes these two triangles congruent by side angle side postulate. So once we know that these two triangles are congruent, we can actually say that the segment OA is equal to the length of the segment OB. Similarly, we can go to the bottom part of this figure and look at triangles OBE and triangles OCE. We can also say that OE is reflexive to OE, and then the length of side BE is also equal to the side EC, since this is a perpendicular bisector, and then also that OEC has a measure of 90 degrees, and then the angle of OEB also has a measure of 90 degrees. So we can also use side angle side to prove that these two triangles are congruent. Once we have proved these triangles are congruent, we can also say that OB is equal to OC. So we actually have three radii, and we know that the radius is equal to OA or OB or OC. Hence, every triangle will have a unique point O that acts as a center of the circumcircle, and also a unique radius that is the distance.
Let's talk about theorem 1.16, where an inscribed angle is equal to 1/2 its subtended arc. So, if you look at this picture, we have points X, Y, and Z on the circle, and we've also labeled the center of the circle as O. And we labeled the angle that the center makes with arc XY, we just labeled that angle A. And we've also labeled angle B, which also subtends arc X and Y. And we're going to prove that that angle is 1/2 its arc, which is XY. So if you look at this next picture, we went ahead and drew another line from the center O to point Z. So we've made two triangles. Well, each of those lines are radiuses. So therefore, OX equals OY equals OZ, since they're radii. So therefore, two sides of each triangle equal each other. So therefore, it's an isosceles triangle. So therefore, we've went ahead and labeled that for the corresponding triangles to the same angles as equal to each other. As you can see, we have angle C and angle C, and for the other triangle, we have angle D and angle D. And we went ahead and labeled the other angle of each triangle as angle E and angle F. So we know that each angles add up to 180 degrees. So from one triangle, we have two angle C plus angle E equals 180 degrees. And then for the other triangle, we have 2 angle D plus angle F also equals 180 degrees. So we're going to rewrite those as angle E equals 180 degrees minus 2 angle C, and likewise, angle F equals 180 degrees minus 2 angle D. So if you add up angle A, angle E, and angle F, it adds up, all the angles add up to 360 degrees, since they make up the full triangle, since they subtend the entire circle. So therefore, angle E plus angle F plus angle A equals 360 degrees. Well, since we've already written down what angle E and what angle F equals, we're going to go ahead and substitute those into the equation. So we're going to get 180 degrees minus 2 angle C plus 180 degrees minus 2 angle D plus angle A equals 360 degrees. Now we're going to rewrite that as 360 degrees minus 2 times angle C plus angle D plus angle A equals 360 degrees. Well, if you look back here, you can see that angle C and angle D actually, if you combine them, equal angle B. So that means angle C plus angle D equals angle B. So we're going to substitute that in the next line here. So now we have 360 degrees minus 2 angle B plus angle A equals 360 degrees. Well, we're going to subtract 360 degrees from both sides, and now we're going to get angle A angle A minus 2 angle B equals 0. And we're going to rewrite that as angle A equals 2 angle B. And divide both sides by 2, we're going to get angle B equals 1/2 angle A. Well, the angle that forms from the center to the arc is just going to equal the arc length in degrees. So, therefore, angle A is just going to equal arc XY. So therefore, we got what we desired, which was angle B equals 1/2 of its subtended arc, which was XY, as in the picture. Well, as a consequence of this theorem, as from the proof of the theorem, we have that angle B equals 1/2 of arc X, W, and Y. And if you look at angle C, the arc that it subtends is X, Z, Y. So therefore, angle C equals 1/2 of arc X, Z, Y. So if you add these two equations together, we're going to get angle B plus angle C equals 1/2 arc X, W, Y plus 1/2 X, Z, Y. Now we're going to rewrite that as where those two angles equal 1/2 of X, W, Y plus X, Z, Y. And if you look at the picture, we have XZY plus XWY equals a full circle. So therefore, it's going to equal 360 degrees. And if you multiply that by 1/2, we're going to get exactly what we wanted, which was angle B plus angle C is going to equal 180 degrees. So therefore, opposite angles of an inscribed quadrilateral equals 180 degrees. Law of sines. Given triangle ABC and its circumradius R, we have that A over sine of A equals B over sine of B equals C over sine of C equals 2R. So we're gonna add point P onto the circle where B goes through the center O to point P. So we're gonna let BP be the diameter of the circumcircle, and it's going to equal 2R. So, for this theorem, we have three cases. First case is when angle A is less than 90 degrees. So since BP is the diameter, it has a degree equal to 180 degrees. So since angle C subtends the diameter, therefore angle C is a right angle at 90 degrees. So we have a right triangle. So, therefore, sine of P equals A over 2R. And therefore, side A over sine of P equals 2R. Well, since angle A and angle P subtend the same arc, therefore, angle A equals angle P. So we finally get A over sine of A equals 2R. And in this next case, where angle A actually equals 90 degrees, so we have triangle ABC. Therefore, since angle A is a 90 degrees, it is a right triangle. Therefore, BC would have to be the diameter. And we're just going to label that side A. So, since A equals BC, which is the diameter, therefore, it equals 2R. And if we just plug that in, where A over sine of A then we also know that since angle A is 90 degrees, sine of 90 degrees is just equal to 1. So therefore A over sine of A equals A, which is equals 2R. And that proves that case. Now, the third case is when angle A is greater than 90 degrees. So, if you look at the picture, we have where angle A is going to be greater than 90 degrees. So, and we've also drawn point P and made quadrilateral ABPC. And we also made where BP is still the diameter of the circle. So, since BP is the diameter, therefore we have triangle BPC is a right triangle with BP as the hypotenuse. So it's the same as before. We have sine of P equals A over 2R. Therefore, A over sine of P equals 2R. So, we know that angle A and angle P are opposite angles of an inscribed triangle. Therefore, we know that angle A plus angle P equals 180 degrees. So, but since they are opposite angles, and due to trig, actually if you plug it into sine, there's still actually going to equal the same thing. For example, we have sine of 30 degrees, which is just 1/2. And the opposite, and its supplementary angle, which is 150 degrees, if you actually plug that into sine, it also equals 1/2. So therefore, if you plug them into sine, they actually equal the same thing. So sine of P still equals sine of A. So therefore, A over sine of A equals 2R.
And now we have finally proved that A over sine A is equal to B over sine B, which is equal to C over sine C, which is equal to 2R, which is the extended law of sines.